All right, good afternoon, everybody. So, good news is we're done with Bash. The bad news is you're going to have to learn how to program in C. So today we start out with the first C lecture. All right, so first of all, what is C? So C is a general purpose, compiled, procedural programming computer language. So procedural basically means it has structural or structured programming constructs. So it has things like loops and if statements, you can declare variables and things like that. Right? All of you should have either taken CISC220 or you're currently taking CISC220. So you've seen the if statements and for statements and while loops and things like that in the Java language. The good news is they're identical in C. Right? So C uses the exact same, Java took the C constructs and uses those for its core language. So that's the good news. Like Java, C has what's called a static type system. And so what that means is that the variable types are known at compile time. Right, so in a Java program, you have to say something like int x equals 1. Right, so all your variables have types. The types are known to the compiler, which means the compiler can do things like check, does the statement x plus y make sense? Right, are x and y both numeric types, for example. C is similar in that regard. You have to type your variables. All variables have types. Right? The compiler tests whether or not you're using the types properly at compile time, for the most part, unless you intentionally circumvent it. Like most programming languages, I guess most procedural programming languages, C also has recursion, so you can write recursive algorithms in C. You'll often see that, or you'll often see on the internet that C is called the high-level language that is closest to the machine as possible. So what they mean by that is that for every construct in C closely maps onto some sort of machine language instruction. So it maps closely onto something that the CPU can actually do. Right? Loops are basically a series of operations that loops can be written as a series of operations that your CPU can understand. Right? So things like multiplying two ints or multiplying two floats, those basically correspond to a single CPU instruction. That's not true in a language like Java or Python, right? So in Java, when you make a new object, a whole bunch of things happen, right? Like literally dozens or hundreds of lines of code actually happen when you use the new operator. That's not what happens in C. Right? So in C, everything's at a much lower level. Okay, so if you click on that link, that will take you to the history of C as written by one of the people who actually developed the language. The original C language was basically developed by two people. And that language is still used today. So if you, somewhere I have these all up. Here we go. So it's this document here, Development of C Language. It's written by this gentleman by the name of Dennis Ritchie. So Ritchie and Kernighan are the two people who developed the C language. You can see that it was right in the abstract. Right? You can see that this language comes from the 1970s. It actually started slightly earlier than that. The development started in the 60s. So a lot of the programming constructs that you use today, even in a modern language like Python, they all have their roots in C or a predecessor of C. Okay, so there are some, the article is interesting if you're interested in history. But there are some interesting things in the article that I want to point out here. One of the people who developed Linux, his name is Ken Thompson. He wanted to create a programming environment. He had a computer, which I'll show you in a second, but he didn't really have any programs that you could run on the computer, which is interesting. So someone at that time, you could buy a computer but not get any software with the computer. And so basically, if you wanted to do anything useful with the computer, you had to program it. So Ken Thompson, he was faced with this, the computer that he was using was this thing called the DEC PDP-7, which is actually a famous computer. in terms of the history of computers. You can see here that the machine he had, so he had 8,000 18-bit words. So that's roughly, what is it, 8,000? So that's roughly 16 kilobytes of memory. That's what he had to work with, right? 16 kilobytes. So your cell phone probably has 8 gigabytes, right? So 500,000 times more memory than his computer did, right? So he didn't have a lot of memory to work with. And so Thomson was the guy who started development of Unix. And his original Unix implementation, he had to write in this thing called assembly, which I'm not going to show you now. I don't know if you ever write assembly anymore in your undergraduate education. Assembly is a lower level language than the high level languages that you use today. Basically, it consists of very primitive operations that your machine that the CPU can understand. Okay, that's his computer that he was developing on. It's basically a big box, right? And it's got a bunch of electronics inside of it. You can see over here, right? That thing that looks like, I guess it looks like a keyboard. That's how he would enter, or that's how you would type into the computer. He has no monitor, right? So you type some stuff in. To get output, there is a printer here, right? So if you get any output from the computer, it ends up being printed out on this old printer. And it's not like a printer that you have today. This was an old printer. It had a ribbon in it, and it was a mechanical device. Right? So you notice the price here. So at the time, $72,000 US, which in today's dollars is about $600,000. That's your computer, no software. Right? There's a, if you Google for the PDP-7, you can find the Wikipedia article for that computer here. Notice that it says, with a cost of $72,000, it was cheap, but powerful by the standards of the time. So cheap is $500,000. Right? Is there anything else interesting about this thing? No, not so. Oh, wait, sales. Okay, so the PDP-7 was described as highly successful. They sold a total of 120 of them. Okay? That's the total number of computers that were sold. So things have changed quite a lot since the early days of computing. All right, so Ken Thomson, so when Ken Thomson was writing the Unix operating system, he was working in this very low-level language. He decided it would be a lot easier if he had a higher-level language to work in. So at the time, there was a language called BPCL, which I also have a tab for. Right? Basic Combined Programming Language. Right? So it was originally intended for writing compilers for other languages, and it's no longer in common use. Right? Now, BPCL is interesting because, number one, it's the predecessor to C. But number two, a lot of the things that you're used to doing came from BPCL. So those curly braces that you use in Java to denote blocks of code, they came from BPCL. Right? So curly braces used to delimit code blocks. Right? That was the idea that came from this language here, right? From 1967. There's something else that they did. What did they do? There's another thing that we use today all the time. Oh, here, the single line comment. Right? So // which you use in Java to denote a line ending comment, right? That has roots in BPCL. Right? A lot of other ideas have roots in this language as well. Okay, so Ken Thomson decided he didn't want to use BPCL. He's going to do something else. So he took BPCL, stripped out a bunch of stuff, and created the language called B. Right? So in B, that's where plus plus and minus minus come from. So when you write I++ or I-, that idea came back. That idea originates from 1969. And then Thomson and Ritchie decided that they wanted to take this B language and develop it further, and thus was born C. Right? You might think that it's called C because C comes after B, but that's not the actual reason. Right? Sorry, the actual reason is, oh wait, I can't, sorry, here we go. So the actual reason is, it comes from here. So it turns out that C is the second letter in the acronym BCPL. So C was chosen as the name of the predecessor to B. And then the predecessor to P, a lot of people, the predecessor to C, the successor to C, people wanted to call P. but that didn't happen. Right? Okay, so in 1973, that's basically when the modern version of C was more or less finished. Right? So the language that you're about to learn is 27, 50-ish years, almost 50 years old now. Right? That book that's right here was first published in 1978. I believe that whoever taught this course prior to me, so that was 3 years ago, was still using this textbook, or that book, as the textbook for the course, which is crazy because this is like the very old version of C. Right. So the books that are on queue that are recommended, they're much more modern versions. They cover much more modern versions of the language than this one does. Right, but that's a very famous programming book for computer programmers. Okay, present time, there's been several revisions to the C language. Right? So 1989, 1990, that's when C was first accepted as a standard. So that's when the actual standard for the language was written and formalized. C99, that's the version of the language that we use in this course. C hasn't changed a whole lot since 1999. It's added a few things, but the changes aren't really large. C 2011 is C11, so that was I guess that's the second most recent major revision to the language. I guess that's the most recent major revision to the language. C17 was a minor revision where it fixed some stuff. Next year is supposed to be C23, so that's when the next major version of the language is supposed to be, the next major standard version of the language is supposed to come out. Okay, so why are we teaching you C? Well, it's because it's used almost everywhere. Right? So almost every operating system, at least part of the operating system anyway, is written in C. Right? So Linux is C, Mac is C, Windows is C and C++, and some assembly. Right? Embedded systems, so all of these little computers, that don't have a screen or a keyboard or anything like that, right? Basically a little computer on a chip. Most of those, but not all, are programmed in C. Right? So in your car, modern car anyway, probably has about 100 computers in it. Most of those computers are programmed in C, or a subset of C. All those modern languages that you love to use, like Python or JavaScript or Java, right? Their interpreters or their virtual machines are probably written in C or C++. Right? The standard Python implementation is C. Most of the JavaScript implementations are C++. Right? Perl, if you've heard of it, Ruby, if you've heard of it, PHP, if you've heard of it, their standard implementations are all C. Most of the deep learning frameworks that you use, underneath the hood, it's all C. And because of that, almost every major programming language can actually call a C function. Right? So you can actually take compiled C. You can take a bunch of functions compiled as a C library, give that to somebody, and then in a language like Java or Python, you can actually call those C functions. Right? Anything related to computer graphics, intensive computer graphics, so modern video games, movies, animations, things like that, probably all involve C or C++ of some kind. Anything computationally intensive is either C or Fortran. Fortran is an even older language than C. And many, 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 many more places, right? So C is really, C is probably it's truly a multi-purpose language, right? It's used everywhere. TIOB is one of these indexes that rank the popularity of programming languages. C has never been ranked below 2 since 2001, right? So it's either always 1 or 2. If you include C++ and C# along with C, then there's no comparison, there's no contest, right? Those are the most common. Taken together, those are the most popular group of programming languages in the world. Okay, so for development in the course, everything should be set up for you already, right? So if you follow the instructions, so if you have the virtual machine, you're definitely set up. If you follow the instructions for setting up Windows subsystem for Linux, you're already set up to do development. If you follow the instructions for Mac, you're already set up to do everything. Right? Basically, you install Xcode and the command line tools on Mac, and you're ready to go. Right? So you'll get a compiler, but you still need an editor of some kind. You probably don't want a plain text editor, so you probably want some editor that's C aware. Visual Studio Code is C aware. If you want to, you can use Eclipse. So if you're on Mac, you can use Eclipse. If you're on Linux, you can use Eclipse. When you install Eclipse, make sure you install the C development tools. Right? I actually recommend that you do this if you can, because the debugger in Eclipse is way easier to use than the command line debugger that you'll have to use elsewhere. If you're in Windows Subsystem for Linux, I don't think Eclipse is an option for you. Unless you're in unless you get Windows 11, and then you can actually run Linux desktop applications. So you can install Eclipse in Linux and then run Eclipse from Linux that way. So if you're in Windows Subsystem for Linux and you're in Windows 10, you're stuck with Visual Studio Code. Right? Debugging is going to be a little bit harder for you. Did you have your question about something?
I was going to ask, do we have to be able to compile it?
Yeah. Yes, it has to compile. I mean, that's the requirement. But if it compiles on your Linux machine, it'll compile in CASLab. Yeah. Similarly, if it compiles on Mac and you haven't used anything specific to Mac, it'll also compile in CASLab. So compiling shouldn't be an issue. The only issue is if you compile for Windows, that may not compile on Linux. Okay, if you want documentation to the C language, so the C language is relatively small, and its standard library is relatively small compared to modern programming languages. Right? So the Java standard library is thousands of classes. Right? Python is hundreds or thousands of classes. The C language is not. It's a few dozen header files. So the language and its library are actually quite small. Either one of these two links you will find useful if you want to find the online documentation for the C language and the C libraries. Right? So those are both very useful. Okay, so what does a C program look like? Well, it turns out it looks a lot like a Java program. So it's made up of a bunch of C source code files. Right? So your Java programs is just a bunch of .java files. Right? A C program is just a bunch of .c files. But there's also these things called header files that I'll tell you about a little bit later on. Right? So normally a small C program is just a single .c file. Right? So normally C programmers call their source code files or name their source code files with a .c extension. Right? It's just plain text, so you can use any plain old text editor to read it. If there's a header file, header files are also plain text. They're typically end in extension .h. Right? For a C program, just like a Java program, you need a main function somewhere. Right? So main function is required in one of the C source code files. Right? So there's hello world in C. Well, this is one version of hello world in C. Right? So you see that there's this funny include statement here. Right? There's what looks like a function. Right? So it is. This is the main function. This is one version of the main function. Right? If you were to look at it, you can sort of guess at what it does, right? Because you've seen Java. So you can probably guess that it returns an int. Right? You can probably guess that it has no parameters. Right? And you can see that return statement that returns 0. So it looks like it's returning 0 somewhere. Right? And now you've got this statement here that prints out hello world. Right? So the function puts is a function that can print a string. Now in C, puts can only print a string. So it can't print a number, it can't print, yeah, that's it. So it can't print a number, right? It can't print a single car unless you tell it. Yeah, it can't print a single car either, right? So it only prints strings. There's another version of hello world that you can write that looks like this, right? So everything's the same except the way we print something is a little bit different, right? So here we're using this function called printf. Right? And it's got this funny, looks like a string here. It is. Right? And then there's another string here, which is the string to be printed. Right? I'll explain exactly how printf works shortly. Right? So we got two different versions of hello world. Now, you can't actually run either of these versions. Right? Because C is a compiled language. Right? So you need a tool called the compiler that takes this program, translates it into something that your computer can actually run. Right? And the notebooks actually go through in some detail exactly the steps that a typical C compiler actually uses. Right? Okay, so compiling is the process of transforming code written in one language to another language. Right? So you can write a compiler that translates C into, say, Java, for example, or from Java into C. Right? Normally, though, when people say they're compiling a language, they're taking the language and turning it into an executable program. Right? So that's normally what people mean. Right? A compiler is just a program that compiles. Right? So there are many C compilers for you to choose from. If you follow the instructions for setting up your computer at home, everything's installed for you. Right? On Linux or Windows, you're using GCC. Right? On Mac, you're using something called LLVM with the CLang front end. You don't actually need to know this, right? That's the compiler that Mac has decided to use. Okay, so to actually compile your program, you need to pop open a terminal and you need to type in something like this, right? So I'm just going to do this for you now. Right, so here, oh, sorry, ls, hello, star. Okay, so you can see here I've got hello 1C and hello 2C, right? The contents of them are exactly what I've shown you, right? So there's hello 1, right? It uses puts. Hello 2 uses printf, right? So if I actually try to run these programs, it's not going to work. Hello 1, it's going to complain, right? There is no hello 1, right? If I try to run the source code file, it's going to complain as well, right? Permission denied. Even if you make it executable, it's not going to work, right? So you have to compile this thing first. So GCC, no, -o. So -o means the name of the output file, right? So I'm going to ask the compiler to produce a file called hello1, right? And then you tell it the name of the file that you want to compile in the simplest case, right? And this is the simplest case. So hello1.c, right? So in other words, ask GCC to compile the file hello1.c and turn it into the executable program hello1, right? If everything's fine, nothing gets output, and you have a program called hello1, which you can run, right? So unlike your bash scripts, right, you don't have to set the executable permission on these. It automatically happens when the compiler generates the output, right? So if I look at hello1, you can see that, oh, sorry, AL, right? You can see that that program is indeed executable. Whoops, sorry, right? Now you do the same thing with hello2, right? So compile hello2 and ask for and output the file hello2, right? And that also works, right? And if you run either one of these, so hello1 prints hello world, right? Hello2, not surprisingly, also prints hello world, right? Now if we go in and edit these programs, so let me go in and edit hello1.c. I'm just going to strike, I'm going to remove the semicolon at the end and save it. Right, so now if I try to compile this program, right, it's going to complain. Right, so if your compiler ever outputs something, right, so if you ever see any output from the compiler, it's important that you not ignore it, because the compiler is trying to tell you something. It's either trying to warn you that something something incorrect might be happening, or it's trying to tell you that there's an error and the compilation has failed, right? So the compiler here says it expects to see a semicolon before return, right? So in other words, it's trying to tell you that you're missing a semicolon here, right? So if you ever see error, that means the compilation has failed. You don't have an executable program. If you have an executable program, it's an old version of the executable program, right? So you have to go in and fix your error. Right, so go back into hello1 and slap in my semicolon, right, and save that, and then go back and recompile. Right, so the process of developing a C program is a lot of editing, saving. Right, don't forget to save. Right, so edit, save, compile. Look at the compiler output. If there's any errors or warnings, address the errors or warnings. Go back, recompile. Save, go back, resave, then recompile. Okay, so let's take apart these hello world program one line at a time. Right? So the first line of our hello world program is this thing that starts with a hashtag and says include, right? And then it's got less than standard io.h greater than. Right? Okay, so whenever in a C program, if you ever see something that starts with the hashtag, right, that's what's called a preprocessor directive. So the first thing that happens when you compile a programmer is, when you compile a program, is that something called the preprocessor runs. Right? So the preprocessor scans your source code file and looks for these things that are, and looks for any directives. Right? So it sees this directive called include. Right? The include directive takes the contents of that file, so standard o.ih, right? Takes all the contents of that file and pastes it into your source code, right? So that little 3-line file I have now becomes many hundreds of lines long because standard io.h is quite long, right? And all of the contents of standard IO now appear inside of that program, inside that source code file, as far as the compiler is concerned, right? Now, the reason we have to do this is because this header file, right, has a declaration of a bunch of functions. One of those functions is puts, right? So inside standard io.h, right, there's a line that tells the compiler what the puts function, I guess what it not what it looks like, what the signature looks like, right? So in other words, what does it return? What is its name? What arguments does it take, right? So if you use a function that's declared somewhere else, right, so not inside your own source code file, you probably have to include another file so that the compiler knows what this other function looks like, right? So here we're using puts. I'm not defining puts. Somebody else has defined puts. So I need to tell my program where to find that puts function, right? Or at least what the function looks like. Right? And so that's what the purpose of the include statements are. So the C standard library is just a bunch of these header files. The way that you use the C standard library is that you include one or more of these header files. Right? And so part of learning how to use C is figuring out what functions are declared in which header files. Right? Fortunately, if you look at the online documentation, it tells you, it's broken down into header files, and inside each header file, and then it tells you what the contents of each header file are. Right? So it tells you which functions are declared in which header files. Okay, so in a modern compiler, the preprocessor is actually a separate program. It's usually a separate program. So it's a program separate from the compiler. Right? So your compiler calls another program to do the preprocessing for it. So as we go along, you're going to see that, So as we go along, we're going to use more and more of these header files. So the other thing to remember is that the less than and greater than sign, those are only used with the standard library header files. So only those libraries that are part of the standard library or part of the standard Linux libraries or standard Unix libraries, those are the only ones that use the less than and greater than. Right? When you write your own header file, right, to include your own header file, you use double quotes. Right? So if you have a file called, if you want to include your own header, you would write something like include my header.h. Right? You have to use single quotes there. You use double quotes there. Right? The reason for the distinction is that the compiler knows where the standard library header files are. Right? So they're not stored in your local directory. They're stored somewhere on your file system, and the compiler knows where those are stored on your particular file system. Okay, so if you want to comment in your program, you've got two choices. So you can use the, well, basically they're the comments from Java, right? So the line ending comments are // right? Multi-line comment is /* and //, right? So exactly the same as Java. That's because Java got the commenting style from C. Okay, and the main function. So every C program, the language here is funny. This is copy and pasted directly from the C standard, right? So basically every C program that you're going to write in this course, it has to have a main function. Right? So the main function is the designating starting point of any C program. Right? There can only be one. Right? So this is different from Java. Right? So in Java, you can write as many class files as you want. Every class file can have a main method in it. Right? I don't think we ever tell you how you actually run a Java program without using Eclipse. Right? So if you actually want to run a Java program without using Eclipse and a whole bunch of files have a main function, main method in it, you have to tell Java which one you want to run. Right? But in C, only one function, there can only be one main function in your whole program. Right? There's two forms of C. There's two forms of the main function. Right? The first one is the one I've already shown you. Right? So main and void, and then the body of the function. The other one that we're going to use more often later in the course is this one here, right? Which looks kind of intimidating if you look at it for the first time, right? This is closest to the one that you would have seen in Java, right? So I guess I'll just tell you what this means, right? So so this version of the main function, you can feed your program command line arguments, right? So you can write a C program that takes in command line arguments just like a bash script will accept command line arguments. Right? argc, that's the number of command line arguments plus one. That's the number of command line arguments. Right? This funny thing here, this char star argv, what looks like an array, that's C's way of telling you you have an array of strings. Right? So in other words, when you pass in the command line arguments, your C program gets them as an array of string. We'll learn how to decipher that later on in the course. Okay? The C standard says that a compiler writer can create other versions of main, but we're not interested in that because we're not writing a compiler. Okay, so the first version of main, or this version of main, returns an int, has no parameters, right? So it looks a lot like Java. You can't do things, you can't put in words like public or static in front of a function in C, right? So there is no public, private, protected, or anything like that in C. There is a static, but it means something completely different in C, right? So it's just the return type, name of the function, parameter list here. Right? Okay, puts is the function that can print a string to standard output. Puts also includes the new line character, right? So \n at the end of the line, right? So puts print a string, goes to the next line, right? So it's like println in Java, right? Unlike println in Java, you can only print a string, right? Now here you can see that a string in C looks like a string in Java, right? So it's denoted by double quotes, right? Anything inside double quotes is a string literal in C, right? Just like it is in Java. Okay, now the second version uses this thing called printf. So printf is formatted print, right? So the way this thing works is the first string contains a bunch of information in it that tells printf how to print the rest of the arguments to the function, right? So %s means interpret the first argument after the formatting string as a string. Right? So in other words, interpret this as though it were a string. Right? Then take that string and substitute it for %s. Right? So printf is going to take hello world, substitute that for the %s, and then print the \n. Right? So notice printf does not print the new line character unless you tell it to. Right? So if you remove the \n, then when this thing prints, it does not go to the next line. Right, which we can do here. So let's just run hello2 again. So notice when you run it, it prints hello world, and then the prompt appears on the next line. Right, if you strip out the \n, recompile. So this is the thing you're going to have to get used to. And so in C, every time you make a change, you have to recompile your program. Right? And that's a big change compared to, I guess, programming in Java, right? Where you can just press the run button and away you go. Oh, I was just about to do something that you're not supposed to do too, so let me show you that as well. Right? Okay, so now if I run hello 2, right, notice that it does not go to the next line. Right? So it prints out hello world, program ends, and then my prompt appears on the same line as the output. Right? So if you want to print something in printf and you want it to go to the next line, you have to put in the next line character explicitly. The other thing you shouldn't do is don't do this. So don't write that. Right? So that tells the compiler to compile hello2.c. Right? Save the resulting program as hello2.c. Right? So what's going to happen here? It's going to overwrite your source code file, which I'm going to do. Oh, actually, this one, that's good. It complains now. Never used to complain. Right? So a long time ago, it would just overwrite that file. Right? That's nice that it complains. That's good. Right? But watch out for that. Right? If you ever be very careful when you're using when you're specifying the name of the output file, that it's not the name of one of your input files, or if it's not the name of one of the files that you don't want to overwrite. So hang on, let me see. There's a whole bunch of files here. So I'm just going to overwrite one of them. Right, so I can blow over array, sorry, 9. Yes, right? So I can compile hello.2.c, and I can blow over or overwrite one of my other source code files in this directory. Yep. And now I can run array9.c. Right? But my old array9.c is now gone. Right? So be very careful when you're specifying the output file for your compiler. It will overwrite whatever you it will overwrite any existing files. Okay, return 0. So why is there a return statement in this main function, right? Because the main function, your program ends, right? As soon as your main function ends, right? So where is that 0 going? Oh, sorry, where is that 0 going to, right? Well, it turns out the 0 goes back to the operating system. And the operating system, so in Linux, that return value becomes the exit status of your program, right? So remember, every bash script has an exit status. Well, it's not just a bash script that has an exit status, it's every command has an exit status. Right? So if I go into here, right? So we can run hello1 again, right? It prints something out, but I can also ask for the exit status of the most recently run. Oh, what happened? All right. That's weird. Oh, what's going on? Okay, sorry about that. I don't know what happened. Okay, so we ran hello1. It prints something out, right? It returns 0 back to the operating system. That's the exit status, right? So if I ask for the exit status of the program, it's 0. Right? If I change the return statement, right? So where's my cursor? Here we go. So I'm going to return 10 in this case. Right? Recompile. And then rerun the program. Right? And then ask for the exit status. It's now 10. Right? So the return statement in the main function is sets the exit status for the program, or for the program. Right? And so a lot of the commands that you use in Bash are written in C. Right? So the way that they set the exit status is by returning a value from the main function. All right, that's a good place to stop, and then we'll start with some more substantial C programming in the next lecture. Yes?
What's the benefit to compiling like this instead of compiling it like VS Code?
Sorry? What's the benefit?
Compiling like this instead of just compiling it in like VS Code.
Instead of compiling in Visual Studio Code.
Yeah.
So if your Visual Studio Code is configured to compile already, then you should do that. There's no advantage. There's no advantage to doing it this way. This is the way you used to have to do it before we had before we had things like Visual Studio Code. Right? If you've already configured Visual Studio Code to do it, then use Visual Studio Code.